My collaborator is Balázs Pozsgai, who's at the Budapest University of Technology. I'm at City University London, and this project is still sort of part of the Form Factory Budapest, like group work calculation, ensemble. So the title is LeClair-Mussardo series for two-point function integrable quantum field theories. We published this like a few months ago, and you can find it on arXiv. Okay, so let's get into business. So if we're dealing with quantum field theory, then an approach or important quantities are one-point functions, two-point functions, and correlation functions. Since if you know all the correlation functions, we know basically all the information from the quantum field theory. So these quantities are important, and they can also be related to observables and experimental results. Like the order parameter can be a one-point function, or in linear response theory, you need two-point functions. And this is where sort of my topic relates to transport, where you need also two-point functions for transport. But I'm going to focus really on two-point functions and calculating them, and not really putting them in like specific setup to do like experimental explanation, but really the object to understand the two-point functions. So since the quantum field theories are really strongly interacting, then it's not a trivial way to calculate these two-point functions or any correlators. It's something you have to do perturbation theory. You need more information, and this becomes even more difficult usually if you consider like a finite temperature setup or finite density or any kind of situation like this. So to get over this problem, I'm going to focus on integrable quantum field theories. Since in these theories we have plenty of nice symmetries or infinite symmetries in the background, and nice machinery that can give us non-perturbative results in quantum field theory. And it's really powerful tools to use here. And there's a hope to have like analytic results for these correlators and other quantities as well. Okay, so the basic setup that we are interested in, that we have a system in like a finite density state. This reference is omega that was already considered by the GHD talks or by Jacopo Maurizio. This can be like a finite temperature, a thermal state, finite chemical potential, or a GGE. And what's important for us that we can describe this state by a beta root density denoted by rho occupied. And theta is the rapidity of these quasi-particles. We also have the density of holes. And we have this constraint for these particles that the total density is related to like this is the derivative of the momentum of the particles, and phi is from the interaction. That's the derivative of the phase shift of the scattering matrix. So this constraint comes from the beta, and that's a beta-Young equations. And on top of this, to really consider one given situation, we should set more constraints. Like for example, if we consider thermal state, then we should calculate the free energy and make a setup point approximation that really fixes us these densities, or we can do GG or any kind of ensemble. And I also would like to introduce one more quantity, this filling fraction, that is the ratio of the occupied densities over the total densities. And this quantity is going to be present in the calculation, and this is what's going to describe as the background linear formulas. Okay, so these are the two guys that we're really interested in. The one-point function in this reference state, and the two-point function with some given separation. For us, the result is going to be only for space-time, a space-like separation is going to even its convergent expression. But these are the guys that we're really after. And we're going to use this form factor approach that I'm going to explain a bit more later. Okay, so basic setup. So let's see what can we do, or how can we sort of. Oh, before that, I just give you an example that if these densities are a bit too abstract, then maybe if you think about the thermal situation, then you have the thermodynamic beta-ansatz equation described by Zamolodchikov for relativistic models, and then you have the pseudo energy, epsilon, that's the log of the ratios of the occupied density and the whole density, and it satisfies this integral equation. That's really the saddle point solution for the thermal situation. Yeah, A is the one particle energy, and beta is the inverse temperature, or finite volume if you want to look at the situation in finite for minute finite temperature. And the situation, the filling fraction is just 1 over 1 plus e to the epsilon. For free theories, this is just the Fermi-Dirac distribution. But here we have really this the epsilon energy that contains information about the interactions. Okay, so let's check a really basic, simple example. One-point function for a free fermionic theory in thermal situation. So you have this thermal one-point function. What you can do by textbook, you just express it like the trace, the density matrix operator, 1 over the partition function. Here beta is against the inverse temperature and H is the Hamiltonian of the system. So if you have this, then maybe you think that, okay, let's calculate the trace in a complete set of states, like consider energy and momentum eigenstates that I denoted by these rapidities. And then you have like an infinite sum, integrals, and the matrix elements of the density matrix and the operator. Since these guys are energy and momentum eigenstates, you know what's the eigenvalue of the Hamiltonian. You just have the energies in the exponent, and you left with the matrix element of just the operator and these integrals. Yeah, and energy is just the m times cos theta, and momentum is m times sin theta, the usual relativistic parameterization of particles. What's a bit problematic with this expression is that, so this is a diagonal matrix element. You have the same particles on the two sides. And in this situation, you can have singularities. When you have plenty of singularities and disconnected terms that you should figure out what should be the well-defined finite result in this situation. And also the partition function is singular. But if you say that, okay, we have these matrix elements, let's sort of expand it with connected terms and scalar products. And if you do it nicely with a bit of finite form regularization, you can end up with a resummation formula where you have the connected part of these form factors, and this filling fraction just turned into this big filling function with the Fermi-Dirac statistics. So it's, if you simplify, you just have 1 over 1 plus e to the minus beta energy. So this is a well-defined finite quantity, and this is for a free fermionic theory. So this is really easy so far, but the question is how to do it in an interactive situation. Because in interaction, we need to sort of modify the filling fraction, and really, I'm not sure that really this is going to be a formula for interaction or not. The connected that doesn't contain any singularities, like you don't have like a lower particle number multiplied by the scalar product of Dirac deltas. I mean, I can write something. So if you have like an operator, let's say with 2 particles, then this is going to be the same guy connected. Yeah. Plus, let's say, theta 2 scalar product. Maybe this is connected. You have the other for theta 1, and you can have like just the, I think, the scalar product and the vacuum expectation value. Yeah. So this kind of expression, but here you have the delta functions in the scalar product that you should figure out. And if you do like this finite form regularization, then some of these delta functions will combine with the deltas from the partition function, and then you will end up with this regular expression. Okay. So this is, yeah, easy way to do it with free theory. So let's figure out what to do with interactive theories. And the outline of my talk is that first I'm going to talk about this integrability, or the ingredients you need from integrability knowledge, like the scattering matrix and the form factors. Then I'm going to show you the one-point function result, the LeClair-Mussardo series, and go through the way how it gets proven, or the proof of the validity. And then I'm going to show the proposal of Balázs and me for the 2-point functions, show some checks, and then conclude. Okay, so integrability. So integrability, you have infinite many conserved charges in the system, And the central object is the scattering matrix, the elastic factorized two-particle scattering matrix, this S theta. We can denote it by this cross and this dot. And it has several properties from quantum field theory, like it is unitarity. That means if you multiply two after each other, it's going to be identity. In writing, it means that S theta times S minus theta equals to 1. You have crossing symmetry when you rotate your head and then change space and time. You have information for the bond states and the pole structures and the residues and their properties. And if you write down these properties for the scattering matrix, you can sort of bootstrap the solution, like find functions that really solve these properties. Then you can match these to actual theories and see that, yeah, we found the non-perturbative full scattering, two-particle scattering of an integrable model. Okay. In this talk, I'm going to consider like diagonal scattering, mostly with one particle. It's that one massive particle. Yeah, for the moment. It's simple to generalize the results for several particle species, but with only diagonal scattering. For non-diagonal scattering, there's still like open questions, what to do and how to do. Okay, so this is really the crucial starting point for integrability. And then if you have the scattering matrix, we can move further and ask what can we do with other quantities like the matrix elements. So these are the form factors, the matrix elements of local operators between the asymptotic states that are energy momentum eigenstates. Yeah, this is the form factor object. An important property of these form factor functions is the crossing symmetry that tells you that you can relate a form factor when you have like n incoming particle and m outgoing with other form factors, like when you have one less outgoing particle, but one more incoming when the rapidity is shifted by I pi. That's how you cross an outgoing particle to the incoming side. But you can have like disconnected terms when any of the rapidity of these cross particles coincide with the original guys. And then the residue is going to be also a form factor with less particles. So by this crossing symmetry, we can relate every form factors we have to the elementary form factors when you only have incoming particles. And this is like a nice function, meromorphic. If it's like a plus I pi, that means there was an original and outgoing particle. And then this has really nice properties due to integrability that are called form factor axioms that I'm going to show you in a second. So these form factor functions in a relativistic theory obey Lorentz invariance that tells you that if you shift the rapidity of every particular Lorentz boost with lambda, then it's going to be the original form factor, and you can get a factor from the Lorentz spin of the operator. For scalar operator, this is not present, so you just have like this shift symmetry for the form factor. You have the exchange property that tells you that if you have two particles going into the form factor, you can sort of exchange them, and that will lead to a scattering matrix factor of the difference of these particles. And you can see this is the cross when you swap two legs of the form factor. Moreover, you have the periodicity property that tells you that if you take this particle, cross it to the outgoing, and cross it back to the other side, that means a 2I pi shift in rapidity, then this particle is going to be on the right side of the operator. And the one more really important, or actually the really crucial axiom for us in the calculation is the kinematical pole axiom that tells you if you have like a particle that comes in a given rapidity and a particle going at the same rapidity, that means that there's an I pi shift between the two guys, then you're going to have a singularity. And the residue of the singularity is told by this axiom. So there's basically two ways how you can separate this on-shell particle from the operator. You can pull everything to the left, that's the one factor, or you can scatter through all the other particles, and that's going to be this product of the scattering matrix factors. So this is the kinematical pole axiom that's really crucial. There's one more that I'm not listing, and it's not important for us at the moment, is about related to poles to bond state formation, or the dynamical pole axiom, but it's not important for us at the moment. Okay, so if you have these form factor axioms, and you know the scattering matrix in the theory, you can try to also bootstrap the solution. That means you can try to find really solutions for these equations, and then it can be related to like actual operators in the theory. So how does it go usually? You take the two-particle form factor, that you can call like the minimal form factor, depending on the two rapidities. And since it's relativistic theory, it's only depending on the difference of the rapidities are just denoted by theta. From the exchange axiom, you have this relation, and from the cyclicity, you have this other relation. And in the knowledge of the secondary matrix, many times you can really write down a function for this minimal form factor that can be quite involved with integral representation, etc. But basically, it can be calculated. And then if you have this minimal form factor, you can make an ansatz that you have like the product of the minimal form factors of the difference of the rapidities with every pairing. You put in the denominator this exponential form that sort of produces you the kinematical pole when there's an I-pi shift between the two guys. And there's the rest of the form factor is going to be this Q polynomial, usually it's polynomial, that's symmetric in this X variables. There's 2 I-pi symmetric in theta, and yeah, symmetric otherwise because yeah, there's all the exchange axioms are satisfied by this term. And then you can try to find like solutions for this Q polynomial by the recursion of the kinematical pole or band state poles. And if you find one of these big polynomials, then there's the art how to match it to given operators and figure out that, oh yeah, we found the operator of the, I don't know, the case of the Szecsenyi tensor or any kind of operator. It can be done in several theories. So you're given by a function that really tells you the matrix elements non-perturbatively of given operators. This is the form factor bootstrap situation. Okay. A bit tricky situation is again these diagonal form factors. When you have like the same particles going out or coming in, you have these I-pi shapes then, and you're just sitting on all the kinematical poles, and it's really singular. So the question is how can you extract some meaningful information from these diagonal form factors? And if you shift these rapidities by a small infinitesimal numbers, you can figure out what's the singularity structure. You have just like the coefficients and these epsilons in the denominator and also some combinations in the numerator. And there's two usual or natural ways to extract finite information. One is the connected evaluation. When you just say that, okay, we take this shifted form factor, we expand this in its epsilon coefficients, and we take the part that doesn't depend on epsilon at all, the real finite part. That's the connected evaluation. There's the symmetric, when you say that, okay, all the epsilon should be the same, so you don't have singularity, and then take the epsilon goes to 0 limit. And that also gives you something that's a bit modified from the connected, but there's a nice relation proved by Poshgai and Takacs in 2008 in their finite volume form factor articles. Okay, so these are two important evaluations that we are going to be present in the calculation. Okay. So the start of the game today is the conjecture. So it was formulated by LeClair-Mussardo in 1999, and they just said that, okay, if we have like a finite temperature one-point function, that you should express it with the spectral expansion the following way. You have the connected evaluation of the operator, dynamic form factors, so it's regular, and you will have the filling fraction from the TBA that you had. And they said that, yeah, this is the finite temperature one-point function. And maybe it's important to note that since it's massive theories that we are dealing with, this expression is sort of like an inherently small temperature expansion, like large beta, because for large beta, these filling fractions are really suppressed for many particles. And also there's a bit of like duality, not duality, but a bit different roles, like all the information from the background or the finite temperature is encoded in these filling fractions, and all the form factors are the usual infinite volume vacuum form factors over here. There's no dressing for the form factor in this formula. Okay, so LeClair-Mussardo made the conjecture. Then was an alternative proposal by Delfino that used symmetric evaluation, and the not dressed energy is not the pseudo energy, but really the energy is over here. So that there was a few years when the people tried to figure out what's good or not good. There was an article by Suller in 2000 when he showed that if you take like densities of conserved current or conserved charges, then you can show that the LeClair-Mussardo conjecture is really valid. It's for dense or for conserved quantities. And then there's the way to sort of go through the proof of the LeClair-Mussardo conjecture. The first step was in this kind of formulation, the finite volume form factors. It was calculated by Pozsgai and Takechi in 2008. Basically, what they did, they took the finite temperature one-point function, plug in the trace with these energy eigenstates, put the whole system in finite volume. They could write down the matrix element, these diagonal form factors that have this form, and then take an infinite volume limit that's a well-defined, no singularities, and everything combines to be nice. So this finite volume expression was important for this calculation. And okay, what we have in this expression? That tells you that if you have like an m-particle finite volume diagonal form factor, it's going to be a sum where you separate these rapidities into two partitions. One of the guys you plug in to a connected form factor, and the rest is going to produce like a density for you, and it's divided by the whole density. The density is calculated from the quantization condition in the finite volume. If you live on a cylinder in finite volume, you can think that, okay, you have this quasi-particle, and let's say that we move around one particle of the cylinder. It's going to scatter in all the other particles and also give a phase shift from the circumference, and it's a periodic boundary condition, then it should be 1, and this quantizes you the rapidities that you can have. Taking the logarithm, you can relate the rapidities to integer quantum numbers. And you calculate the density from this mapping. So basically, you have this quantization condition. You take the derivative matrix and take the derivative. That's the total density of the particles. And these sort of restricted densities are the situation when you erase columns and rows belonging to some rapidities from this matrix and then take the determinant. Okay, so they conjectured this formula, checked it numerically, and then using this, they showed that the LeClair-Mussardo conjecture is winning over the Delfino in the third order. The next step was when Pozsgai used the same formula but with a different approach. He said that, okay, we have this finite volume formula, but then make a thermodynamic limit, like taking infinite many particles and also infinite volume, limit at the same time. And he were able to show that this is really going to arrive to the LeClair-Mussardo conjecture with the good form factors, and all these densities are going to combine into these filling fractions of the integrals. And then the last step, sort of in this way of the proof, was when last year Zoltán Bajnok and his postdoc showed that the diagonal form factor formula is like a consequence of the off-diagonal finite volume form factor. So it's sort of proved the diagonal formula where and Balázs derivation was based on that. So this is like sort of finishing the proof of the LeClair-Mussardo conjecture. Okay. I just show like an alternative expression of the LeClair-Mussardo conjecture, namely when instead of connected form factors, you use symmetric form factors. And to do so, you have to introduce like a new function next to the filling fraction that's just this exponent of this form. And sort of it can be seen like if you had this connected formula, this is a partial resummation of that way. Like you take out some terms from the connected form factor and plug it into this extra exponential sort of filling. Okay. Yeah, so LeClair-Mussardo also had a conjecture for the two-point function, but that was shown in several articles that it's not really valid. Also in just a basic point why it's not really good, because they didn't really specify for higher particle terms how to take how to deal with singularities, and yeah, it was not a good proposal. But back just for a minute for the one-point function, I want to show you that this LeClair-Mussardo series for massive theories can be really convergent fastly. So I'm just going to show you like numerics and some pictures that when we evaluated this LeClair-Mussardo conjecture. So for this evaluation, we took the so-called T2 model. It's like the M23 minimal CFT perturbed by the phi 1,3 operator. This is a non-unitary theory. It has two primary fields with these weights. It has two particles in the infrared, this relation. And there's a relation between the perturbation coupling and the mass scale. We know the scattering matrix of this theory. described by these guys. Well, yeah, this is like sort of elementary S matrix vector, and also the form factors are known, but I didn't want to show it over here. So since we have the form factors, S matrix, everything, we can really calculate the LeClair-Mussardo series or series, but we need like another numerical method to cross-check, and for that we use the truncated conformal space approach. Truncated conformal space approach that was mentioned last week by Matti Lencic, and it's basically taking the conformal field theory Hilbert space, calculating the perturbing operator in that basis, then truncating this Hilbert space and diagonalizing numerically the Hamiltonian. So it's like a variational method to calculate like the spectrum in finite volume and also matrix elements. And then I just show you the pictures. So here in the horizontal axis is like m times L, because in relativistic theories, for a thermal situation, you can look instead of like a finite temperature situation, like a finite volume situation. For the 1-point function, it's really sort of the same. So instead of temperature, we have the cylinder. You can think like m beta instead of L. Here's the expectation value of the phi-1,2 operator. The dots are the TCSA results, and this first solid line is just the vacuum expectation value. Then you add one more term from the LeClair-Mussardo conjecture. That's when you have like a type 1 particle going around the cylinder with this filling fraction. This is getting closer, and it's getting better. Then you add more terms when you have one type 2 particle and two type 1 particles. So all the ones means that type 1, 2, type 2. And you add more and more terms, and you see that it's really getting closer to the TCS result, and over it's like 10 to minus 8 or really high precision. But you also see that the LeClair-Mussardo is really like a low temperature, large volume expansion, because for small volumes or large temperatures, the convergence is not that fast because the damping of the filling fraction is not so strong anymore when it's smaller than 1. But still, it seems like, yeah, it works and it's happy. Okay. Let's go to the 2-point function situation. What can we do with a 2-point function? So there's an approach by Poshgay-Takács to use the same kind of finite volume regularization that you put also this 2-point function in finite volume, evaluate the trace and plug in a complete set and write everything with form factors and finite volume form factors. Then you can rearrange the terms to see that you really have like finite quantities in the large volume limit, these D and M's, and it's like a double sums of these quantities. I didn't want to write them because it's really big terms containing form factors and integrals, etc. This NM subscript basically tells you that how many particles you take from the trace and from the intermediate complete set of state, roughly. Okay, so this is like a systematic expansion and calculation, but it's really tedious and it's not really good to go for higher particle number. And also the information from the finite temperature is really separated into different terms. It is not really compactified or not really obvious what's the contribution from the background. So this was not really another way to really write LeClair-Mussardo series for 2-point functions. But then there were serious articles in the 80s by Kramer, Tucker, and Wilkinson, where they sort of considered 1D Bose-Gas and 2-point functions of the field operator, and also they take the separation to 0 and then ended up with the density operator. And sort of, in a way, they derived the LeClair-Mussardo series in this situation, and also showed that for the 2-point function, this 2-point function, or the 2 operator form factor has the similar kind of structure as a 1 particle form factor. Namely that it also has similar singularity or kinematical pole properties. So that's the sort of the origin of our proposal that tells you that if you have a 2-point function, let's look at these 2 operators like a 1 bilocal operator. If the separation is not that big, then you can still think that it's sort of localized in space-time, and you can calculate matrix elements of this guy. So we calculated the form factors of this bilocal operator, and then the important is to show that it satisfies the same form factor axiom, same kinematical pole. And if it does, then there's the hope that we can just plug it in the LeClair-Mussardo 1-point function, and we reduce the 2-point function calculation to the 1-point function calculation with a bit more tricky bilocal form factors and more info. So that's the idea of the conjecture, or the proposal. Okay, so let's see if this goes through or if we're going to fail badly. Yeah, so what we did for the first calculation to really, let's say, brute force calculate these bilocal form factors. And for that, you can take the Fourier operator algebra. It formulates this, like if you exchange two creation operators, you have the scattering and all the other guys. And using these operators, you can sort of expand any local operators in the basis of this creation. So in the book of Smirnov, and also recently in this algebraic quantum field theory formulation by Simon Kadamuro, they really showed that this expression exists and it satisfies the form factor axioms, and it's really nice and working in a good way. And the coefficients in the expansion are related. Oh, is it working? Okay, sorry. So it's related to the form factors. When you have like a small shift in the rapidities, like infinitesimal shifts, that sort of tells you that, so these coefficients are sort of like a distributional limit of the form factor functions that you can have over here, because of these shifts, you don't really have singularities by themselves. These k factors are just coming from the shift operator in space-time, so just a phase factor with the energy and momentum of the rapidities involved. Okay, so we have this expansion. So let's look at this bilocal form factor, two energy eigenset two sides, and let's see what can we do. If you plug in this expansion for both of the operators, we have lots of Fourier of creation and annihilation operators, but we can easily commute through everything on everything and see what's going to be the really remaining term at the end of this form factor. And we arrive to this. So this is in a way the bilocal form factor of an operator that contains form factors of both of the operators with different particles, some scattering matrix factors, and this factor from the shift operator. But maybe it's nicer to have like this visualized version and understand the formula in this way. So what happens that you have the two operator, O1, O2, and you have some rapidities on the right, either in the set of the A set, and the outgoing are in the B set. And the way to calculate this bilocal form factor is you have to bipartite both of the incoming and outgoing rapidities. You take a part of the incoming to go into the O2 operator, some to the O1, and the same to the outgoing particles. And then you will have a sum for all the intermediate rapidities between the two operators. So you have like this infinite sum for them, and also integration for the rapidity of these intermediate guys. And you also have like some scattering matrix factors from the computation. And the scattering matrix factors can be understood really easily. So this guy is nothing that you take the original state that the particles are ordered like θ1, θ2, θn. You do the bar partition, and then you have to sort of scatter through the particles each other to bring to each of the operators. This is just rearranging the rapidities in the order to separate these two sets. The same for the B rapidities or B sets. And the third factor is just the factor when the guys who are going into O1 and the guys who are going, the Bs who are going to O2, they all scatter in each other. And that's just this last factor. And even important to mention that these form factors all contains like specific shifts to be regular expression. Yes, and yeah, you can also like, if you have like a space like separation, you can do these mu contours and they have a bit reformulated expression that behave nicely and don't contain any more shifts, but then some S matrix factors are modified, but maybe that's more easily usable, let's say. Okay, so the question is that, okay, if we have these brute force bilocal form factors, are they really good or not? But we were able to show that they really satisfy the exchange properties for both the incoming and outgoing guys. They satisfy the Lorentz transformation, but then it's a bit, the form factor is also transformed because it explicitly depends on the space-time, the second operator. But the really important and crucial part for us that they satisfy the kinematical pole axiom the same way as for the single operators. So it's the same kinematical pole as we had before. And this is really important for us to be able to use the LeClair-Mussardo expansion. Okay. Yes, so since we have these form factors, they satisfy the same properties, we can just write the two-point function, like a usual LeClair-Mussardo with a filling fraction, but not the connected form factor of this bilocal object. Or the symmetric, but then we have this other factor. So this is the same LeClair-Mussardo, but with this more complex object. So what kind of arguments we have that this formula is valid other than it satisfies the kinematical pole? You can think about like an operator product expansion. So that these two operators are sort of closed. We can expand it on the basis of other primary fields and operators. And if this expansion is really convergent, that's not proven, but sort of we believe, then we can use the LeClair-Mussardo for the one-point functions, and then the sum is going to arrive to the two-point functions. It's a bit more hand-waving, but intuitively says that if OP is correct, then it should be, everything should go through. The other more direct check is that, so I showed you this double expansion from finite form regularization. We can check our results compared to that because we calculated some terms already for this guy. And to really cross-check the two results, basically you have to expand this filling fraction, like in a nice way for this thermal situation. And then you can see that if you sum up some terms in this double sum, it's just going to be really the connected bilocal form factor when you don't have any particles on the incoming outgoing. If you sum up this contribution, then it's going to be the integral of this one particle connected bilocal. And you have other guys. We calculated these two and they match perfectly the previous results. So it's proven that it works for a few terms already. One more important property that you expect from a two-point function is the cluster property. And for that, if you take the symmetric way of writing this guy, and then you take the separation of two operators really big, the space-like way, then you can sort of argue that all the integrals between the operators are going to be zero, so there's no intermediate particle. And in this way, these two guys are really going to be separated into the product of two LeClair-Mussardo series for the one-point function. So this is also an important cross-check that it's valid. Yes, and you can take non-relativistic limit on a formula, check previous known results, and yeah, for 1D Bose-Agassiz calculation, and everything seems to work properly so far. Okay, so let me conclude. So what we did to learning from the LeClair-Mussardo series, we said that, okay, for a two-point function, we can look at this object like a bilocal operator and calculate form factors that has the same analytic properties as the usual form factors. So we can write it like a LeClair-Mussardo series. We checked the previous results and argued that it should be correct. And yeah, that's our proposal for this two-point function that can be used for finite temperature or finite density or the kind of beta root density describable states. But there's still like sort of asymmetry because we also still have like form factors that are not rest, but really the infinite volume, and all the information of the background is put in the densities or the filling fraction. So maybe there could be like a way to resum these form factors and also have like rest form factors. We don't know how to do it yet, and that's like an open question. And also a question is that where is it applicable, this whole formula? So believed for the moment that for space-like separation, this bilocal operator is really, this infinite sum is convergent, so it's well defined, and we can really put it in the LeClair-Mussardo. But the question if you can use it for other separations or not, or what kind of situation is it actually applicable or really worth to calculate these guys or not. So thank you very much for your attention.
Okay, thank you. So questions? no, it is. I have a question about your results and similar results for lattice systems. I mean, there are form factors at finite temperature for spin 1/2 Heisenberg chains, and these expressions look much more complicated. These are multiple integrals and so on. So, what is, you cannot answer the complete relation, but what is noticeable is in these more complicated formulas for lattice systems, the temperature is built in everywhere from scratch. And your formulas are relatively simple. I mean, you have these n-particle functions that satisfy functional equations independent of temperature, and then you multiply them with some Fermi factors or some dressed Fermi factors. And this is rather simple. So well, one question could be, can you expect, or do you expect that the lattice formulas will terribly simplify in a low temperature limit, or can you think of, let's say, non-unique solutions to the to the functional equations? I mean, you presented a minimal scheme, so there are two ways out. So either lattice formulas simplify drastically, or the continuum formulas or results are not unique.
I would think it's unique. I mean, if this whole sum is convergent, then I think it should be sort of unique, this bilocular form factor. I can imagine that there's really like a way of resum a result to a more compact way when we don't have these infinite many integrals, but maybe less integrals and really dressed form factors. But I don't know how can be really dressed form factors formalized in QFT, because like there was the work by Benjamin Doyle on this finite temperature form factor axioms, but he only solved those axioms for free fermions, if I'm correct. But he also had like a result from this generalized hydrodynamic result method recently. I don't know how to relate a result to his, but we sort of started to look into it a bit, but that's really a different formulation. And I think over here he might have probably resummed form factors, but I'm not super sure. But with lattice models, I'm not super familiar with all the finite temperature form factors. Yeah, maybe some resummation can help. Like also, like I think for Sinch-Gordon, there's this fermionic basis calculation by Smirnov, when sort of also for the 1-point function is sort of resummed in a nicer way, but that's like a fraction of 2 1-point function that he has. So, but I don't know how to. I think it's only valid for maybe Sine or Sinch-Gordon his results. I don't know how can we do similar kind of resummation over here. That's still an open question.
So I understand that you did not study these continuum limits of lattice models in detail. But
no, I didn't. But I think maybe Balázs has more idea about this because he works a lot with lattice models. But yeah, I personally don't know the answer.
Something that might be also important in relation to what you ask is that what he was talking about was diagonal theories.
Yes.
So theories with diagonal scattering, whereas in the Heisenberg model you're thinking about, the QFT equivalent of that is Sine-Gordon, which is non-diagonal. And in Sine-Gordon, even in the simplest case, even at 0 temperature, the form factors usually are expressed as an integral. They have integral representations, and they are much more complicated than what he presented. So I think it might also be that somehow makes a big difference. Yeah.
Yeah, exactly, because I think for the non-diagonal scattering, even the finite volume diagonal formula is not superly shown or proven or understood. So I think also the LeClair-Mussardo series for non-diagonal scattering is partially known, but not really in a way. So like I think that maybe Gabor Takács and others had like an article when they had like this finite volume regularization expansion for the non-diagonal situation, but they don't really have the LeClair-Mussardo for non-diagonal situation, as I understand.
All right, if one question.
Check your operator product expansion, but I think the form factor expansion is, so to say, a long-distance expansion. And wouldn't you have problems then? I mean, you have, let's say, the first terms in the form factor expansion, and then you use operator product expansion checks, which are good in the opposite limit.
Yeah, I think that So the OP argument, you don't really need to calculate this explicitly this biological form factors. So I think it's like an intuitive hand-waving argument. Yeah, we didn't really check precisely to do the expansion. Yeah, that might be true that it's a different kind of limit where it's applicable.
Okay, I think we can thank the speaker again.